Recorded is rolling. It's Thursday, September 8th. So we've got this hang on a second. Okay, so yeah, want to make the most of the day. I know I'm only here for 3 days this week, so I did want to get a lab in, but we're gonna have to put that off on Monday. You know what? Let me show you guys. Hold on. Let me pause this again. All right, so you guys see this projectile launcher here. So you can change the angle here. You can there's a protractor where this bob will hang down and show what angle it's at. Right? You guys know remember how to read protractor? You guys use that, right? And you can click this, click, right, and then pull this thing. Pow, and out it goes. Right, now, can you guys imagine? You could use this like a cannon. You could either set this on the ground to launch it at an angle, or you could set it on top of a cliff and aim it straight out. So we'll do something like that on Monday. At least wanted to throw that in front of you guys so you can see what that setup looks like to think about in a few days. But we'll do a lab that's related to that cannon Monday. All right. So today, I want to start making some graphs. I'm going to take you guys through a range formula. We'll look at some solutions. I know you guys were working in teams yesterday. I want to go through some of those with you guys today. Solve some problems. Most of you guys have turned in the quiz that was due a few days back. If you haven't yet, then still wait for a few days later before I get those back to you guys. But if you have already, then upgrade that for you guys. Interim 1 actually ends today. We are an 8th of the way through the entire school year. So grades close to June. Double check all your classes, make sure you got everything in. All right, let's get rolling. All right, so you guys remember this page here? All right, let's make some graphs related to this scenario. All right, so cannon, top of a cliff, fire straight out. Let's do 3 graphs. Want to do? Yeah, let's do 3 graphs. Okay. Go ahead. This way. So graph number 1 is going to be, let's go height versus time. Right. Now I have to define which direction is up. So let's call down the positive direction. Okay. And we'll define the top of the cliff is 0.0. So if I do height in meters versus time in seconds, right? So at time 0, it's at the top of the cliff, which is position 0. And if down is positive, it only continues to move downward, right? Right. So what does that graph look like? Can I show that? So everybody just drew a parabola, right? That's what you guys just drew, right? Because you guys have seen that many times. In fact, the answer is just right there on that poster, right? Height versus time. Okay. Isn't this just the vertical component of the motion? Say the vertical displacement, which is the exact same if you just dropped a ball from the edge, which is again the answer is right there on that poster on that ball, right? Boom, just like that. Okay. What if I do this? Right? Because since you guys are in AP, you have to be able to field different definitions, different scenarios. So what if I have the exact same scenario? So nothing's physically changing, but I just changed the definition of what's up. Let's call up positive and down is negative direction. Right. Let's say that the cliff height, I'm going to define as h naught, like an original height. Right. And we'll call the valley elevation equals 0 meters. Okay. So the valley's down here at 0 meters. At time 0, we're going to blast. Okay, remember, this scenario we're looking at. This is all we're doing, right? Okay. And h naught, I'm going to call the top of the cliff. Okay. Okay. So it's the same scenarios we did, but I'm just changing some definitions. Okay. Well, now what does this curve look like? Height versus time.
Parabola?
Yeah, it's still a parabola, it's just upside down. Right? So you're counting the seconds off after 1 second, it falls 5 meters, after 2 seconds, it falls 20, then 45, then 80. Yeah, it's gonna be still a parabola, just like that. Okay. In fact, you could take its physical motion, because you guys can imagine what this looks like, right? That's a parabola, that's a parabola. Do you think you could like stretch the time axis and then overlay it right on top of the video and be like, could be an exact match? Yeah, you guys can see that, right? Okay. Okay. So these could be the same answer to the same scenario, or but just with different definitions of what's up and what's down. You guys see that? You guys see this one is just the upside down version of this one. Just take it upside down. You guys see that? Okay. All right, let's do so same scenario, but instead of doing height versus time, let's do the vertical component of velocity as a function of time. Okay. Now I have to define some direction as a positive direction. Let's go down as negative. Yeah. So usually I do the opposite in your notes, but yeah, again, you guys are AP, be ready to field both ways, because AP could ask you both ways. In fact, one of the questions they asked, they did a 3-parter and they changed the definition in the middle of the setup. You guys remember that? Okay, one was progress checks. Okay. So let's go the vertical component of velocity as a function of time. I already messed up my graph. That's all right. Here. Okay. So when you blast out at time 0, it's the cannonball's moving how fast up and down?
0.
0. Yeah. So the point 0, 0 exists, right? At time 0, there's 0 velocity, right? And then if down is negative, then doesn't the cannonball continue to fall faster and faster in the negative direction? Right. So I should have made this a 4th quadrant graph, not a 1st quadrant. So put it here. Okay. In fact, what does that look like? Can you guys graph it before I do? Oh, you guys can stay a step ahead of me. That's a good indication. You know what's going on. Wouldn't it look exactly like that? Right? Which again, the answer is still that poster. It's just the upside down version of that poster, right? Okay. Because that poster on that wall over there, well, it's linear motion, but we're just focusing on the vertical component, so same idea, right? But that poster, up is, or I should say down is positive, right? Versus here I'm saying down is negative. Okay. So it's just the upside down version of that. Okay. Right. So after 1 second, it's going 10 meters per second in the negative direction. After 2 seconds, it's up to 20, 3 seconds, 30, 4 seconds, 40. Straight line. Okay. As long as you ignore air drag. Let's also do one more graph. Let's do the horizontal component of velocity as a function of time. And here I'll say, let's call it the right is positive. Okay, so now we're interested in left-right, right? Like a left-right type motion. So if I blast this cannonball to the right, it's going in the positive direction. So this is all gonna be positive numbers, right? Everything's gonna be positive. So I can definitely make a 1st quadrant graph for this one. Okay. What's v sub x as a function of time? This could be in meters per second. This could be in seconds. So at time 0, let's say the cannonball is just being blasted from the cannon, and maybe it's like, well, I'll call it v blast, whatever that is. So I'll give you this point, right? So at time 0, it's blasted really fast, leaving cannon. Right? And then let's say it takes a few seconds while it's a projectile sailing through the air. Right. What does the rest of that graph look like? Horizontal line? Oh yeah, horizontal line. Exactly. So you guys all got that, right? Because you guys are saying after 1 second, it's moved to the right that fast. After 2 seconds, it's moved to the right that fast. After 3 seconds, right? So there's no change, right? Because there's no horizontal force, right? Gravity only pulls vertically, not horizontally, right? So this is sub x. This is in the horizontal direction, right? And also we're ignoring air drag, which we've been doing all along. Yeah. So there's no horizontal force. So just keep doing what it's doing, right? Okay. You're right. Acceleration versus time actually would take that same shape, because acceleration would also be constant, right? So yeah, if you said vertical acceleration, which would be gravity, yeah, it would also look like that too, wouldn't it? Okay. Now this is horizontal velocity versus time, because And that also looks like that. Okay. So the story I usually go with is if you're up here in a blimp, like way up a kilometer up, you watch, right? And you're pretty much just focused on the horizontal component of the cannonball, just watch it go across the field. Would go pretty much across the speed, wouldn't it? I mean, that's what that graph says. Right? It's not going to speed up or slow down horizontally. Okay. Okay. So you guys can on those graphs? That's good. All right. Next thing I want to do with you guys, I want to do something that's a little bit more in. You gotta be kidding me. Okay. Let me pause this thing. All right. If you're watching the recording at home, I'm gonna pause this. All right, recording resume. Let's do quick fire drill stuff.
At this time, it is necessary to evacuate to silent areas. Please evacuate to silent areas.
All right, you guys know we're gonna shut off the store. We're gonna your left. You guys remember the bus is? All right, we're gonna line up. There's number 29, and you guys gonna find Griffin on a stick out there. You guys are gonna find Griffin on a stick. Griffin on a stick. All right. So I will see you guys outside. All right, recording is resumed. All right, you guys did a great job for the fire drill. That was efficient on your guys' part. Everybody showed up. All right, so back to this. Now, we just did a bunch of graphs for this situation. We're looking at what's going on strictly vertically and strictly horizontally, which is how we've been breaking down projectiles last few days, right? We just like analyze what's strictly vertically, strictly horizontally. Okay. I do want to do graphs for also this scenario. You guys remember this one? Okay. So let's do some similar type graphs. Here, let's put 3 side by side on a page here. Some European looking flag. Let's go height versus time. Let's go the vertical component of velocity as a function of time. Thank you. And let's go the horizontal component of velocity as a function of time. And let's have up be the positive direction. Let's say the positive vertical direction. Let's say forward or to the right is the positive horizontal direction. Okay. Okay. I'll make some axes here. Okay. So we got height in meters as a function of time in seconds. We got the vertical component of velocity, meters per second, as a function of time in seconds. And the horizontal component of velocity, meters per second, as a function of time in seconds. All right. Okay. Now, what is this graph gonna look like? Remember what the scenario is. The scenario is I've got this cannon down on the ground. It's gonna fire a cannonball. It's gonna also land on the ground. Ooh, so it lands in the same vertical position that it started, right? I see, from ground to ground. Right. Now, what do those 3 graphs look like? I should really change ink color to do, because I know I got blue lines all over those place here. Okay. All right, so for height versus time, suppose at time 0, it starts on the ground. Maybe I give you guys that point, right? Okay. And then sometime later, it's also going to land on the ground, so that point must exist, right? Okay. In fact, you know what? Did you guys have this first graph done? Okay. Did you guys draw an upside down parabola? Is that what you guys did? Okay. Because time's ticking is going up, 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 slower, 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 and then time keeps ticking, it comes down faster, faster. Okay. In fact, you know what? That graph is exactly that shape, isn't it? Okay. Well, I mean, you could like warp the time axis. I bet you can manipulate the time axis, and you could fit it exactly on top of this because they're both parabolas, right? Can you do that? Okay. And if I defined down as the positive direction, then you would just like turn this upside down, right? How about the vertical component of velocity versus t? Okay. Now guys, this cannonball leaving the cannon, is it going up really fast? Right. You guys, since you have this in your notes from a few days back, does anybody remember exactly how fast it's going up for these numbers? You guys see it's a 3, 4, 5 right triangle? Okay. 80. Yeah, 80. Isn't it going 80 meters per second strictly upward? Because that's 100 times sine of 53 degrees, right? Right. Okay, so I could throw like 80 meters per second up here and say at time 0, it's leaving at 80 meters per second. Right. Like 80 meters per second. Okay. Then after some time, actually after how many seconds does it take to reach the peak? Well, is it going up 80 and then 70 and then 60 and then 50 and it takes 1 second to change by 10 meters per second? So does it take 8 seconds to reach the peak? Okay. So after 8 seconds, it's moving how fast vertically?
0.
0. Yeah. Right. So the cannonball is in motion at the peak, but only horizontally. It has no vertical component of velocity, right? It's not going up or down, right? Okay. And then after another 8 seconds, isn't it about to crash land? How fast is it going strictly vertically at the crash?
Negative 80 meters per second.
There you go, negative 80 meters per second. Exactly. To go to negative 80. Right, put a point right there, right? Okay, so we've got 3 points on the graph anyway. What does the rest of that graph look like? Straight line. Yeah, it's a straight line. Okay. Guys, all your velocity versus time graph for constant acceleration are going to look like that. Okay. Oh, you can tell me what's the slope of this line?
110 minus 7.
Yeah, negative 10 meters per second squared. There you go. Right, it's just whatever free fall gravity is in. It's just we're on Earth. Yeah, that would be negative 10 meters per second squared. Right, am I true? Right. Right. It's going slower on the way up because it's tending towards 0, and it's going faster on the way down because both the magnitude of the velocity is getting further from 0. Right. Is that okay? Why that graph looks like that? Right. And finally, the horizontal component of velocity versus time. In fact, since I'm referring to this exact example that has some numbers on it, how fast is it going across the field?
60.
60 meters per second, right? Right. Did you guys do 100 times cosine of 53? Right, you got 60. Or maybe you're thinking it's a 3, 4, 5 right triangle, right? Because it's 53. However you did it, you get 60 meters per second. Right. Now that's how fast it's going across. Is that the same all the way across? Like after you count off like some number of seconds and some more seconds until it crashes like 16 seconds later, it's always going 60 meters per second across the field. That's a constant value. Right. Yeah. If there's no horizontal force, there's no horizontal acceleration. Yeah. So that's also called a law of inertia, right? If there's no force in that particular direction, it's just going to keep doing what it's doing. Okay. You guys get those graphs? Okay. All right. Let's switch over and do. All right. I have a prepared packet for you guys, which is especially lucky today because fire drill and whatnot. Right. So I want to do something a little bit more extensive than AP usually does, because this is like AP is supposed to be a college level class. Let's definitely do like a college level question. Right. So suppose you have actually this exact scenario, right? And what if you're wondering, I wonder what angle you have to angle the cannon at to send the ball the furthest distance, like see this X, right? Or maybe more general, the way we're going to approach that is we're going to first come up with a formula. What's the relationship between this angle and this horizontal displacement X, right? The X could also be called the range. If you ever open up the physics books and see the word range, right? They're referring to this, okay? Like how far does it go before it lands, right? Now, let's do some thought experiments before we start running the numbers. Like if you take this cannon and you aim it up at 90 degrees, so if you take this angle all the way 90 degrees, where's the cannonball going to land?
0.
Yeah, at position 0, right? It's going to destroy your cannon. Let's pull up our cannon. Oh no, it's a bad experiment to start with. Yeah, so the X would be 0, right? What if you take your cannon and aim it at 0 degrees, straight horizontal? And maybe theoretical physics, the cannon like is at level 0. So doesn't the cannonball like immediately hit the ground pretty much, right? Or it wouldn't go very far, right? So that would also be X at 0. Okay, so what I'm thinking is like the more I angle this up, it's going to go further until some optimal angle is reached. And then if I keep going up further, it's going to start coming back, right? It's going to go up and then start coming back. And I wonder, another example that ties into this is suppose you're in a baseball throwing contest with your friends, right? You can't affect your maximum throwing speed, but you can affect the angle that you throw it at, right? So who can throw the baseball the furthest? Right? I wonder what that angle is, right? Well, if we had some formula that told us the relationship between these two, then we could use that to figure out the optimal angle, right? So let's do this. Get this out of the way. Right, so here's our setup. Right, look at that. Looks like that. Oh, I'm just calling V like the blast speed. Right, so just plain V is gonna be the blast speed. Right, not gonna worry about putting the subscript on it. Right, so whenever you see V in this, there's a several page proof going on here. Right, now here's something that we did. Even go back to last Friday. Right, is we broke that into components. Like that's the first thing you want to do. You say, well, if you blast something up and to the right, how much up and how much to the right? But that's just sine and cosine components, right? That's what we just did with this guy right here. You guys said, well, at a 53-degree angle, 100 meters per second, that'd be 60 to the right and 80 up, leaving the cannon, because you did exactly this to figure that out. 100 times cosine of 53 is 60 meters per second. 100 times sine of 53 degrees is 80 meters per second, right? Okay, so now we're able to analyze this, right? Now we're able to go into our physics analysis because we know how fast to cross and how fast up. Okay, you guys get that? Okay. Remember what our goal is. Our goal is to figure out what's the relationship between these two, this x and this theta, right? So that's like eyes on the prize. Okay. Let's come up with a formula for x. Can you guys come up with any formula for yeah, question?
Maybe like halfway the horizontal. I mean, it would not have to be twice horizontal because isn't the maximum like kind of the midpoint?
You're right. The max is the midpoint, right? So
And that's what
oh wait, are you talking about like this triangle? Okay, yeah, no, this triangle is really just a proportion. You could make this triangle any size. You can make it small, you can make it big. Because all this triangle really refers to is what's going on right as the ball is leaving the cannon barrel. Right. So it's just a proportion thing. It's just kind of coincidence that it kind of happens to be pretty close to the midpoint. Yeah. So you can make this triangle small or big. It's just a proportion question. Yeah. All right. So go do this. What I'm covering up next is a formula for x. It doesn't have to be fancy. I'm just looking for something very simple. Can anybody tell me, can you write any formula for x? Any formula for x, just as a starting point. X equals what? Yeah, just well, since it's horizontal, there's no acceleration. Isn't it just horizontal component velocity times time? Right? Right. There's no 1/2 at squared or anything like that because there's no acceleration, right? The whole 1/2 at squared, you guys know that's only vertical, right? Right. Okay. So it's just x equals vt. But the v is this v sub x, right? It's just how fast it's going across times however much time it's in the air. Isn't that true? Right. But hey, if we're ultimately trying to get x in terms of theta, shouldn't I sub out this v sub x in terms of theta, which is v times cosine theta? Right? Can you guys write that next step before I show you? Right? Stay a step ahead of me through this whole process. Stay a step ahead of me. Right? Did you guys write that? V cosine theta times t? Right? You guys see what that would be, right? So blast speed times cosine theta is how fast it's going across, times the amount of time it's in the air would tell you how far it went. Is that true? Okay. Now here's where that theta and that t are related to each other. Because think about this: if theta is really small, the time in the air is going to be really small. If theta gets closer to 90 degrees, that would like maximize the amount of time it's in the air. So that theta and that t are related to each other. They are not independent of each other, right? So thinking ahead here, what I'm going to do is I'm going to say, hey, can I somehow substitute out this t in terms of theta, right? You guys get the idea? Right. The fact that these two variables are related, right? If I could substitute out that t in terms of theta, then I could have just x strictly in terms of theta, right? Well, and also the blast speed, but we're treating that as a constant. It can just blast whatever it blasts. Okay, you guys get that idea? Okay. So where are we going next here? Okay. Well, we need some kinematic formula to figure out what's the relationship between theta and time. Now, this is only one way to do it. This is not the only way to do it, but you can take that second kinematic equation, you can modify it like this, right? You guys see how you can get this, right? Df equals v naught plus at, but it went to vertical, so it did in the vertical direction. And then if you blast it up, the cannonball up, the gravity's pulling down. I went ahead and took care of the negative sign already. I just embedded it, right? And then instead of a, it did g for gravity, right? Right. And then you guys know in the y direction, it's the blast speed times sine of v. of the angle, right? From that last picture. Okay. I could also say this, I know that however fast it's crashing vertically is the same as it was blasted vertically because it went from the ground to the ground, right? Again, this is not the only way to figure out this relationship. This is just one, probably like several ways you could do this, right? Do a little bit of algebra here, and you can get t in terms of theta, and it looks like that. Okay. Okay. So this was a whole side quest just to get t in terms of theta. This is just one of several ways to do it. Okay. So I used the second kinematic equation as an entry point, did some substitutions, did a little bit of algebra, switcheroo, and there you go. Okay. So if you want to know the amount of time it's in the air, well, I do see that's proportional to the blast speed. Like if you double the blast speed, it's going to double the amount of time. I see it's inversely related to the gravity. If you have stronger gravity, less time is in the air. That also makes sense, right? Really strong gravity, be back on the ground almost immediately. Okay, and then some do with the sine of the angle. Okay, suppose that can make sense. Is that okay? Okay. Now that we've got the substitution piece, let's substitute that back into that previous expression. Remember these two variables are related, so I want to substitute out this t in terms of theta, and now we can do that. You guys get that? Okay. All right, so next line. Okay. So remember we had this, right? And we said, well, that's actually that if you substitute, right, v sub x in terms of the blast speed and the angle, right? And then I want to substitute out that time. And then we just did the whole second kinematic equation to come up with this expression, right? So boom, 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 got all this, right? All right. Hey, that v and that v, that's the same v, right? Can I put those guys together? You do that, right? Now here's where, do you guys remember trig identities from like pre-calculus or trigonometry? Okay. Some of you guys maybe? Okay. This part in parentheses, there's a reason I grouped this together. Who remembers what this is equal to? We're just doing a little math trick right here. It's a double angle identity. You guys remember sine 2 theta? Yeah. Okay. Right. Yeah, you guys remember this, right? Sine of the double angle is equal to 2 times sine times cosine, right? So maybe it's not absolutely necessary to do this, but we're going to take advantage of this to solve an optimal angle situation later, right? So if you do that substitution, you get what's called the range formula, right? So let's read the music of this range formula, because I know we did a little bit of tricky math from beginning to end to get to this point, but piece by piece, you guys can do it. You say, okay, well, I know this physics, I know this trigonometry. If you use double angle, do some substitutions, it all pops together. Okay? So here's what this says. This says if you want to know how far you're blasting a cannonball, x, horizontal displacement, also called the range, it's the range formula. Okay. Well, if you know the blast speed of the cannon, square that, divide by the gravity field, and multiply by sine of twice the angle to the horizontal that you have the cannon in. Okay, they'll tell you exactly how far the ball goes. Okay, great. You guys get that? Okay. Do you think you guys could here? Suppose maybe you're like out with military one day, like, hey, let's destroy that tin over there. And you know what x is, and you know the blast speed of your artillery, and you know the gravity field of Earth, 9.8 meters per second squared, right? And they say, hey, you determine, figure out how we have to angle this cannon. Do you think you could do that? Do you think, here, well, I'll do this verbally with you guys. I would take x, I would cross multiply the g, I would divide down the v squared. And then how do you undo a sine? Inverse sine, exactly. You guys could do inverse sine, right? And that would be equal to twice the angle. And so you just divide by 2. You guys could do that, right? Right? You could take this, just do a little algebra switcheroo and solve for theta in terms of all these other things, if you had to. I bet you could do that. Okay, so that's all fine and good. We got ourselves a range formula, right? But I want to take this an extra step. Show of hands, how many guys are in calculus? Calculus. Ooh, that's about half the class. Okay, so this next step we're doing is maybe the only like sort of explicit calculus step that we're going to do this whole class, but I want to at least give you guys some crossover exposure. Okay, you guys know that calculus is about rates of change, right? Instantaneous rates of change. And one thing that you can do with calculus, therefore, is solve optimization problems. And this is a great example of that. Because if you get back to the question, like if you want to maximize x, there is some optimal angle between 0 and 90 degrees that would do that. I wonder what that angle is, right? So we're about to do some calculus here. Oh, but by the way, are you guys doing derivatives yet? You guys doing derivatives?
So,
You're still on what?
so,
Okay. Well, there's something cool I want to show you guys. You know, I'll just tell you, and then someday in your calculus class, you'll see like, whoa, you guys see this green, that green poster up there, right? So if you look at that top equation, x equals v naught t plus f a t squared, right? If you take the rate change of position, isn't that what velocity is, right? So in calculus, rate change, the term for that's called derivative. If you take the derivative of that top equation, you get the second equation. So someday you guys will see that, you're like, whoa, Griffin's right again. Let's do. Okay, guys, I got 30 seconds to show this to you guys. So if you take the rate change of x with respect to theta, anyway, long story short, you get this equation. If you graph that x versus theta, it's I know this looks like a parabola, it's not actually a parabola, it's a part of a sine curve. Or and then if you want to maximize x, isn't that like saying the rate change of x with respect to theta would be 0? Let's say like the slope of the line right there would be 0. So if you set this piece equal to 0 and you solve for theta, the answer is 45 degrees, right? So at a 45-degree angle, that will maximize the range. Okay. All right. All right. So yeah, didn't do everything I wanted to do today. So, but we'll make the most of it. All right. You guys have a great rest of your day, and everything's gonna work out. Everything will be all right.